Hello, my lovely students. So here is our first set of notes. I have two sections in here. I'm going to cut it and make two videos. So these might be a little long, but they're supposed to substitute for lecture. I make kind of fill in the blank notes, so there'll be spots for you guys to write your work, write your thoughts, put a star and write a question. I'm going to upload those blank notes and a link to this video. And my hope is you guys watch this before coming to class, so in class we can focus on your writing assignment and your web work. And get the boring, like, listen to her go over the basics, not in class. So here is our starting basics, is a relation. So a relation is a set of ordered pairs. Now, when you're mathematically minded, ordered pair, your brain automatically goes to numbers. But a relation does not have to map numbers to numbers. So it is just taking two sets of data and creating a correlation. So the relation is the arrow saying this first thing maps over here, this second thing maps here, third thing maps here. That's what a relation does. It just tells you where stuff points. A function is a special type of relation. A function is a relation in which each possible input value leads to exactly one output value. So we say the output is a function of the input. So when we say a function of x, x is the input. A function of y, then y is the input. So that of is always telling you the input. So f of x is often written f of x, despite the typo in the book. So any of the values that are inputs make up the domain. Any of the values that are outputs make up the range. For a lot of our mathematical functions, these end up being all real numbers, maybe with some restrictions, maybe just the positives. It depends on the function. So a good analogy for a function is to think of a vending machine. When the machine is functioning properly, I press the button, I get something out. When it's functioning properly, whatever button I pressed, I get the same thing out every time. A dysfunctioning machine, when you press the button, you get more than one thing out. So don't think of this like the buttons have to match. Think of this like a vending machine where I have pictures of animals and I'm going to get a drink out of it. So I push the cat, I get a water. I push the cat again, I get a water. Okay, cat gives me water. I can check it a bunch. Nope, it just gives me water. Cool, cat works right. I check dog. Dog gives me Dr. Pepper. Good. Now, if I press bird and I suddenly get a Sprite and a Coke popping out, we got a problem. That machine is no longer functioning properly. So that is what you want to take away with the idea of function is when I do an input, when I press a button, I only get one thing out. The thing may not make logical sense to the input necessarily, as long as I consistently get the thing out, then we're good. I don't ever want to push kitty cat and get water and a Dr. Pepper. Now it could be I come back tomorrow, I push kitty cat and I get a cappuccino. Okay. Somebody messed with the machine while I was gone. That's fine. It's a new function, new thing. Now, one of the things the book looks at is when we have these two sets, they often call them A and B, and they represent them in these weird, like, oval shapes. Here's A, here's B, and then the relation is the thing that maps stuff in A to stuff in B. So when we have these two sets and we have this relation defined, sometimes there's kind of a counter, like, inverse relation. We do literally call that the inverse. That'll map things from B to A. So if we like directly reverse whatever relation we have, we can look at it the other way around. And sometimes we start A to B, that's not a function, but if we look at the other way, it might be a function. So you have to consider which way these mappings would go or which ways the relations would be functions. So here, I came up with two examples to kind of explain in more detail what I'm talking about. So here we have a relation that's mapping a flavor of ice cream to a person who likes that flavor best. All right. So we've got one set is ice cream. And then another set is people. All right, so what is A and what is B? However you want to label it. The labeling here does not matter as long as you pick it and you're consistent, which means write it down, show your work. So I'd probably add something like, all right, A is here, ice cream flavors. B is here with people. So if I have a relation that is mapping ice cream flavors to people. So there's my A and my B. I could also have a relation that maps people to their favorite ice cream flavor. So when I'm mapping ice cream to people, so I could have, let's say, vanilla here. I like vanilla. That maps to me, but I'm sure there's more than me that likes vanilla. So this guy's probably going to map a whole bunch of ways. So is this a function? I'm saying vanilla is my input. My output is suddenly multiple things. So A going to B, not a function. But B going to A, when I change it around, I'm saying a person, I'm going to map it to their favorite ice cream flavor. By definition, I am forcing them to pick a single flavor. This will force this to be a function. So we're not going to allow any ties. So when we look at this in reverse, that other person likes vanilla, I like vanilla, Bob down here likes vanilla, we're good. Each person here is mapping to only one thing back in ice cream. So that is a function. Whoop. Sorry, I have a button that erases and I keep hitting it. We could also have a relation that connects a Spurs player to their jersey number. So player to number. I'm old school. That is a number sign, not a hashtag. Yeah, I'm that kind of old. Hopefully you guys giggle. So just talking about what's the A here. A is all the players. I pick a player. Boom, I can get their jersey number. That way would be a function. I am not of a sports nut enough to know if the reverse is true. I don't remember if we hold jersey numbers individual. Like, I think we do for some, but I'm not sure if we do them for all. So the other way may or may not be a function. I'd have to do research on it. Now, function notation. They wrote this y equals f of x. That's how we read it. We could read it as y is, for the equal sign, a function of x. So that f with parentheses is function of, and then x. So x is representing the input here, or what's sometimes called the independent variable. And then y is going to represent our output, which is also sometimes called the dependent variable. It's called that because it depends on the input value, on the independent variable. All right, so we got a question in the writing that talks about this. And I pulled this from the book. You can see it says example 4. So hopefully you guys like at least skimmed the book before you started watching the video. If not, maybe go do that. because there's a whole bunch of stuff in there. I'm just giving you guys that highlight reel. So a function n equals f of y, or n is a function of y, gives the number of police officers n in a town in year y. What does f of 2005 equal 300 represent? So a sentence like this, a question like this is asking you to interpret, and 9 times out of 10 interpret means what are the units? Like write a sentence so these numbers make sense. So when I look at my format here, f of y, f of 2005, okay, so 2005 is a y, and then I check my sentence, y is a year. All right. So in the year 2005, and then f of y, let me pick a different color, we'll go back to pink, equals n equals 300. So that 300 is an n number. I go find my n, and it tells me it's the number of police officers. And then it goes on to say in a town. So in the year 2005, there were 300 police officers in this town. So there's a fancy math. There's all the words it takes to say the same thing in math, given the sentence before defining the units. So represent or interpret usually means write us a sentence that explains the answer, where it's coming from, what does it mean? All right, so if we are given a function for a formula for a function, we can evaluate. The key word here is evaluate. So those of you guys who had 1073 or me for 1073 last semester, hopefully vaguely remember we talked about evaluating, and then we compared it to the word solving. So evaluating is when I take a value, put it in, and figure out what the value of the function value will be. So the phrasing is often evaluate the function at a number. So at 2, at -7, at pi, whatever. But it's telling you whatever it's at, that is our input value. And then we're just going to work and figure out the output value that goes with it. So here's our lovely example, several. So the first one, given this function, it tells us evaluate the function at x equals 2. All right, this is the word way of saying f of 2 equals, and you got to answer. What's f of 2? Well, I know f of x. So if I'm going to figure out f of 2, I'm going to put the 2 where all the x's go. I write this a little bit weird, especially because of my colors. So I'm just going to take my function formula and give me a sec here. I'm going to erase the 2. Let me put the x in. X squared plus 3x minus 4. So what we're going to do now is everywhere there's an x, and I wrote an x. So everywhere there was an x, I'm going to go back and put parentheses with a space. So I'm going to put the parentheses there. I'm going to put the parentheses there. And now I'm going to erase the x's. So now my function, my machine, takes my input. In this case, it's going to be the button press 2. And the function gives us directions for what to do with the input. So this one tells us square the input, add 3 times the input to that, and then subtract 4. So it's just giving us a weird dance move. All right, so we're going to square the 2, we're going to add 3 times the 2, and then we'll just subtract 4. So this is going to be 4 plus 6 minus 4 is 6. Down here, my next evaluate is f of 1. Same song, second verse. F of 1. So there's my thing squared plus 3 times thing minus 4. Let's fill in our thing. 1 squared is 1, plus 3 is 4, minus 4 is 0. Cool. And that's okay. 0 is a number. It's perfectly fine output for a function that maps numbers to numbers. Now, our input doesn't have to be a number, though. All the function is doing is saying square the number, add 3 times the thing, square the thing, add 3 times the thing, and subtract 4. That thing could be whatever we want. If I want the thing to be a banana, I would have banana squared, whatever that means, plus 3 times a banana minus just 4 things. I don't even know what they are in relation to banana, but that is what we would do. So when we do f of a, we are going to have a squared plus 3a's minus 4. And we're actually going to do the difference quotient in a minute, so that's why I asked for f of a and the f of a plus h. So a plus h is a little uglier because now our thing is not one letter, one number, it's an expression. It's got more math in it. So whenever we need to substitute something in, do careful substitution. So we're going to carefully insert this, which means we're going to practice safe math. And those of you who had me know what's coming up, I call the parentheses the condom of mathematics. So always wrap it before you insert it. Yes, yes. All the groaning. I can hear it from the future. It's lovely. And let me, make a little more room because I write so big. All right. Since we're actually going to have to do something with this, we need to clean it up a little more, get rid of the parentheses. So a plus h squared, that is a binomial squared. We're going to need to FOIL and multiply that out. So a plus h times a plus h. So you can FOIL, you can draw the box method, however you want to do it, as long as you consistently get your answer. Now remember, on tests, you're only going to get your scientific calculator, not a graphing calculator, not your phone, not your computer, just your scientific calculator, the provided formula sheet, and the test pages in front of you. So I just want to kind of prepare you guys for what to expect when the test comes up. We will talk about the formula sheet as we go through the semester so you know what's going to be there. So this a plus h, you're going to have to know how to multiply it out. So a times a squared. Then we have a times h. And then we have h times a plus h squared. All right, a times h times a, multiplication is the same forwards and backwards, so those are really two of the same thing. So this is a squared plus 2ah plus h squared. Now up here I have this 3 that needs to be distributed through. So plus 3a's plus 3h's. And then we just carry the minus 4, and I'm just going to write that down here. All right, so there is f of a plus h written with no more parentheses. What a disgusting mess. Now, we're not often going to ask you to do this kind of crap, but in the beginning of calculus, you are going to learn about limits, and then you're going to start learning about derivative. And the long form of the derivative, where the derivative comes from, starts from this different quotient. So here, the difference quotient is just put up there as we call this the difference quotient, and isn't it beautiful? Oh, yay. Okay. All this is a really fancy way of writing the slope of a line. So we did slope last semester in 1073. Hopefully you guys kind of remember rise over run, or the change in y over the change in x's. But remember now, our y's are function values. So if I have f of x2 minus f of x1, there's my y values, and then x2 minus x1. Now check out what happens. Instead of my x2's, sorry I had parentheses up there, but I'll put them down there. I'm going to put a plus h. And then for my x1's, hopefully you guessed it, it'll just be an a. So f of a plus h minus f of a over a plus h minus a. Well, I actually have some like terms on the bottom. So a minus a is 0. 0 plus h is h. So we're actually just going to end up with, I'm just going to erase, h. And look back, there's the difference quotient. So it's a very fancy name, a whole ugly, disgusting fraction, but all it really is the slope between 2 points. You guys have been doing slope for years, hopefully. Maybe not recent years, but it's in there. So that is what we're going to calculate next. See, determine the difference quotient for the above function. So let me grab my loop here. Control copy. I love using a computer. And then down here, control paste. There we go. So there's our f of a plus h. More space. All right. Minus. Now let's go find f of a. So we had a squared plus 3a minus 4. Now I can write all over h. That gets very tedious since we got to clean up the top first. So I'm just going to out front here label this as delta y. Or you could write f of a plus h minus f of a. All right. So the first thing that we need to contend with is that minus sign. Before I can try to put anything together, I need this to no longer be subtraction with a parentheses. So right now, this minus sign needs to apply to everybody in there. So that is my first step, is I'm going to go through and take out the parentheses by distributing. So we're going to have a minus a squared minus 3a's, and now it'll be a plus 4. And then, since I was extra lazy, I think, yeah. All right. Now we need to get rid of things that are the same. So I see an a squared and a minus a squared. I see a minus 3a and a plus 3a. I see a plus 4 now, and there's that minus 4 there. Now notice, everything on the right, everything that was f of a, canceled. It was in there in f of a plus h. I just had to go and find it. So now we're going to write down our leftovers. So I have 2AHs plus H squared plus 3Hs. All right. Now to finish out the difference quotient, all I got to do is divide by H. So let me give myself a little bit more room. And if you actually took calculus, like you get it, you know what the derivative is. We don't technically know what limits are in here. We don't technically know what the derivative is. We're just stuck with our algebra. So our difference quotient, we have 2A. Now I want you to notice, once we canceled out f of A, everything else left has an H. It should. If it doesn't, you made a mistake. So the next thing we're going to do is factor out that H, since they all have it. So I will have 2AH, well, my H is up front now, so that's just 2A's, plus one of the H's is up front, so this is just an H. That way H times H is H squared back, and then plus 3. So our difference quotient is take that and divide by H, and I factored it out, so boop, boop. That is the difference quotient for that crazy function we started with. Now, if you look at that, you might be like, Liz, that's not the derivative. No, it's not. That's the difference quotient. The derivative is when you take the limit as h goes to 0, the h goes away, and you get 2a plus 3 or 2x plus 3, whatever. We're not doing that in this class. All we're responsible for is what we just did right here. So you need to be able to produce 2a plus h plus 3 and produce the work. This isn't just about answers. You guys need to do the work, need to understand what you're doing. So you don't have to show me every little step, but you do need to show me some steps. Okay. Now, here is our comparison. So we were evaluating before. We had a whole bunch of values. We put them in for the x. They were inputs. We got the output that it resulted in. This question, like a question saying solve f of x equals 12. This is not saying x equals 12. This is saying f of x equals 12. The 12 here is not an input, it's an output. So it's asking us to figure out what's the x value that will produce 12. And it could be more than one. It can be a function and have multiple x values go to the same y value. That's okay for a function. So if I have kitty cat gets water, dog gets water, bird gets water, that's fine. Apparently I found the water machine. It's a boring machine, but it is still functioning. All right, so this one here is telling us to solve h of p equals -2. So h of p here is p squared plus 3p, so I'm literally going to take p squared plus 3p, and then instead of h of p here, I'm going to put the -2. And now I have an equation all in terms of p. It is a quadratic, so we're going to have to remember how to solve quadratic equations. And the first thing for solving quadratic equations is get it equal to 0. So we're going to add that 2. Now, if you are not comfortable with factoring, quadratic formula will completely work here. This one though, since the p squared doesn't have a number in front of it, the factoring shouldn't be too bad. So that is where we're going to go next. I'll still keep that 0 equals. P squared can only be p and p. 2, there's only two things, 1 and 2. And then if I have my outside 2 times p, so 2p plus my inside 1p would be 3p's, so these are indeed equal. So I have my two factors. I know here this is saying they multiply to equal 0. The only way for a product to equal 0 is if at least one of the things is 0. So either p plus 1 is 0, or p plus 2 is 0. I don't know which one. And as a mathematician, I don't care which one. They're both the right answer. And literally both. If you only have one, you didn't finish. Now, there are the occasional quadratics that only produce one answer. That's fine. But I'm just saying, like, unless you write the reason why you didn't solve for the other one, like the other one was negative, so I didn't need it. In Mathland, we get annoyed when you don't finish. Even though Mathland has nothing to do with reality. All right. So those are the p-values that produce -2 as a function value. If I plug in -1 into my original function, that'd be 1 plus 3 times -1. 1 minus 3 is -2. If I plug in -2, -2 squared is 4. 4 plus 3 times -2 is -6. 4 minus -6 is -2. They both work. Okay. Now, sometimes we can also be asked to solve a formula for a variable, or we asked, is this a function? And we're just given this random formula with letters all over the place. So the way we tell if something is a function of a value is if we can write it in terms of that value. So in terms of the input. So whatever my output is, I want to be able to get that by itself without any weird mathematical quandaries happening. So when we look at this guy here, x plus y squared equals 4. Does this represent a function? Maybe. Now notice I added to this. Can it be written as a function of x? And then I added as a function of y. So when we say, is it a function, we make the assumption x is going to be our input. That's just the mathematical niceness. We're lazy. But x doesn't have to be the input. We could swap it. We're not going to do that often. But when we talk about inverses, that kind of will happen. So if this can be written as a function of x, then I want to get y alone. So I'm going to try to take that formula and get y by itself. All right, so I would minus the x. I have y squared equals 4 minus x, okay. And then the next thing I would want to do is square root. Now, when we draw in the square root, one of the big reasons I use another color, we're drawing it in, we don't know if we wanted the positive or the negative root, so we have to write both. So y is plus or minus this square root of 4 minus x. So if I plug in a value like 0, 4 minus 0 is 4, square root of 4 is 2, but is it going to be positive 2 or negative 2? I don't know. Both of those would work as an ordered pair in the relation, but as a function, this does not work. My x equals 0 is wanting to map to positive 2 and negative 2 equally. That is a problem. That is not a function. So this cannot be written as a function of x. Is it a function of y? I don't know. Let's see. So asking, is it a function of y, is asking us to get x alone. Can I get x alone? Yeah, just minus the y squared and x is by itself. Well, that's what we're going to do then. Okay, so this can be written as a function of y. If I pick a y value, put it in there, I will only get one x value that goes with it. Our mess up before was we had 0 for the x and we got positive or negative 2. Now 2 is my input. 2 squared is 4. 4 minus 4 is 0. 2 only maps to 0. -2 also happens to map to 0. So this way it is a function. But if we were trying to write it as a function of x, it didn't work. And we know that because we got that plus or minus. Anything that allows that possibility of more than one value, that's what makes it not a function. All right. So many things. Now, sometimes the book is going to represent functions not just as a formula, but as a table like we see here. It could be a graph or the formula or the equation like we normally see. You do need to be able to kind of read this value and understand what's being asked, how to interpret it. So we just did evaluate f of 2, evaluate f of 1. Well, now we're evaluating g of 3. But instead of a formula, I have this table. All right, so g of 3, 3 is the input. I look, my table has the labels n and g of n. 3 is n. So I go over here and look, there's my 3. And the table tells me 3 is mapping to 7. So g of 3 is 7. Cool. Now, same song reverse. G of n equals 6. So 6 is a g of n number, not an n number. So I look, I get an 8, nope, 6. Oh, there's a 6, but keep going. 7, nope, 6, aha, 8. There is more than one correct answer for the solving. That's okay. So n equals 2 or 4. Just writing it as a list. All right. Now the other way we can read it is by looking at a graph. This can be a little weird mentally, but follow with me. So we got f of 2. So f of 2 is telling us x is 2. It's asking what's the function or the y value. So I'm going to look on my graph at x equals 2. My function value is 1. So we would say f of 2 equals 1. And that's the same thing as saying the ordered pair 2, 1 is on the graph. Those are equivalent to each other. Same. Now our f of x equals 4. This 4 is a function value. So that's a y value. So when I look at my function axis, it's actually labeled f of x here. F of x equals 4 is here. So I look like so, and I can see there's 2 points. So we got -1 and 3. So x equals -1 and +3. Those are the x values that will produce 4 as a function value. All right, I'm going to pause it there. So I'll cut this into 2 videos.